Good evening, everyone. This is Pushparaj H. So, welcome to the class. In today's class, we'll be studying about the power systems. In this power system, we'll be dealing with the chapters fault analysis, voltage profile, control. Is that my audio is audible? Okay. So before going into the class, so let me give some introduction about the Ekeeda Educator Online platform. So here in this Ekeeda platform, it's a golden opportunity for all the engineering students who want to score good CGPA in the academics, right? And even the GATE aspirants too. Because once you get subscription to the Ekeeda, you get more and more benefits regarding your education. So I request you all to once go visit ekeeda.com, then you get variety of passes. If you buy a pass, you will be able to access the study materials for complete 5 years. Okay, so there is a code called EKGOLD. By using this code, you get free trial of access for 3 days. So try this once, okay, and go through the availability of Ekeeda online educator platform, whatever the availabilities, what are the materials available there. Okay, once you get subscribed, right, once you get subscribed, you will be getting many ready made PDF notes for each and every subject of your respective branches, right? And even you can interact with educators directly. All the educators are well experienced, and even doubt clearing sessions will be available. One-to-one doubt clearance will be available, and there are so many videos available in the Ekeeda app. Okay, so even you can download the Ekeeda app through Play Store and Apple, right? And there is a gate blog. Visit this blog, that is ekeeda.com/gate. So students, overall my suggestions to you all as is to get subscribe, buy the pass in Ekeeda, and make your dream come true of getting good marks in the academics, and also to crack great examinations with very good rank. So I wish you all the best, and let's move on to the class. Okay, so hi, hello to everyone who all are watching this video. Just put a message so that I can see who all are in the class. So in today's class, we'll be discussing about the fault analysis, voltage profile, control. So before going to the fault analysis and voltage profile control, so we'll be solving a few test questions conducted by the Ekeeda for the students that we are going to clear the. If you have any doubts, you can put a message in the chat box. Clear. So coming to the first problem, that is a 22 kV 400 MVA generator as the reactance of 0.3 pu. That is the value of reactance on the new base of 25 kV and 200 MVA will be, right? A 22 kV 400 MVA generator has the reactance of how much? 0.3 pu. The value of reactance on the new base of 25 kV and 200 MVA will be, the options are given 0.116 and 0.32, 0.58, 0.232. So we have to find out which is the right answer here. Okay, so what will be the right answer? So we'll see now. So as we know that we have a formula to find this. So before that we'll be writing solution for this. So the formula is like this: pu, 1 minute, per unit new, that is PU new is equals to per unit volt into kVA, sorry, kV volt divided by kV volt by kV new whole square into MVA new divided by MVA old, right? So this is the formula here, right? Now per unit new is equals to PU volt, means a 22 kV 400 MVA generator has the reactance of 0.3 PU, right? So this is our PU volt. I will write here given. Actually, I should have written for PU volt is equals to how much? 0.3, right? And kV volt is 22 and kV new is given, that is 25, and MVA volt, that is equals to 400, right? And MVA new is equals to how much? 200. So these are the given data. Just directly we have to substitute the values into the formula. So the main thing is you have to be perfect with the formula, right? PU new is equals to PU volt into kV volt divided by base kV base volt divided by kV base new into volt square into MVA base new divided by MVA volt. So PU volt is how much? Base value of PU is 0.3, that into kVA old value is how much? 22 divided by 25 whole square, that into new is how much? 200 divided by 400. So if you solve this, so the answer for this 0.3 into 22 by 25 whole square into 200 by 400. So the value of per unit, new value of per unit will be 0.116. So in the option, which is the first option, that is 0.116 PU is the right answer. Clear? Understood? So next, moving on to the next problem, that is the per unit value of a 5 ohm resistor, right? A per unit value of 5 ohm resistor at 100 MVA base and 10 kV base voltage is, the options are 0.05 pu, 0.5 pu, 5 pu and 50 pu. So let us write the solution. So what is telling? The per unit value of 5 ohm resistor at 100 MVA base and 10 kV base voltage is, 10 kV base voltage is. So we have to find out the new PU value, right? Now base, write like this, base ampere is equals to base VA divided by base voltage, right? I is equals to, that is base ampere is equals to base VA divided by base voltage. So what is our base VA value? That is nothing but 100 MVA, right? 100 MVA. So I can write here, that is base VA. Base VA means 100 into 10 to the power of 6. Right? I can write like this, 100 into 10 to the power of 6 divided by base voltage is how much? 10 kVA. This can be written like this, 10 into 10 to the power of 3. Right? In place of kilo, that is K, I have given 10 to the power of 3. In place of M, that is mega, that is 10 to the power of 6. So if you solve this, 100 into 10 to the power of 6 divided by 10 into 10 to the power of 3. So what will be the answer here? The answer we get is, right, 10,000. So this is our base ampere value. Then we can find out the base impedance now. So the base impedance is equals to base voltage divided by base ampere. Base voltage divided by base ampere. So what is the base voltage value we have? That is 10 kV. 10 kV can be written as 10,000. Right? 10 into 10 to the power of can be written as 10,000. What is the base ampere value we got? That is also a 10,000. So if you calculate 10,000 by 10,000, what will be the base impedance? That is nothing but 1 ohm. Clear? Now, PU value, per unit value, is equals to 5 ohms divided by 1 ohm. Then what will be the value of new PU value? The new PU value is equals to 5 PU. So here the right answer is option 3, that is 5 PU. Right? Next, the per unit impedance of a circuit element. The per unit impedance of a circuit element of 0.15. The per unit impedance of a circuit element of 0.15 if the base kV and base MVA are off. So this is very important point here. If the base kV and base MVA are off, then the new value of the per unit impedance of the circuit element will be the new value of per unit impedance, right? Per unit impedance of the circuit element will be, the per unit impedance of the circuit element is already given, that is 0.15. Okay, now he's telling that if the base kV and base MV are off, then the new value of per unit impedance of the circuit element, what will be the new value of per unit impedance of the circuit element? Okay, so there are the 4 options, that is 0.075, 0.15, 0.30, 0.60. Okay, now solution for this. So you know that base ampere 1 is equals to base VA, right? Base VA divided by base VA 1 divided by base voltage 1, right? And whereas base impedance 1 is equals to base impedance 1 is equals to base voltage 1 divided by base ampere 1, base ampere 1. Clear? Next, PU value 1 is equals to actual impedance actual impedance 1 divided by base impedance 1. Right? So these are the the per unit impedance of the circuit element of 0.115 means the PU value is PU value 1, that is 0.15. Then actual impedance divided by base impedance, that is PU value. So he has given that per unit impedance of the circuit element is 0.15. So I can write here per unit value 1 is 0.15 PU, right? Okay. So now one is equal to 0.15 PU. So now base ampere, next step is base ampere 2. We'll take it as base ampere 2 is equals to 0.5 into base 0.5 into base VA1 VA1 divided by 0.5 into base voltage is equals to, so 0.5 into base VA1 divided by 0.5 into base voltage 1 means, since he is telling that if the base kVA and base MVA are off, okay, so we have taken here 0.5 into base VA1, 0.5 into base voltage 1, so that gives to, that is nothing but base ampere 1, right? Base ampere 1. Then base impedance, base impedance 2 is equals to 0.5 base voltage 1 divided by base ampere 2. Zero 0.5 base voltage 1 divided by base ampere 2. Therefore, PU value 1 is equals to actual impedance, right? Actual impedance 1 divided by base impedance 2. Then, so PU value, that is, we know that it is 0.15, right? 0.15. Next, base impedance 2, that is 0.15 into 2, right? Then 0.15 to 0.15 into 2, if you calculate, we will get that is 0.30 PU. So the right answer, that is option C is the right answer. That is 0.30 is the right answer. Clear? So next, that is 3 generators rated 100 MVA. 3 generators rated 100 MVA, 11 kV, have an impedance of 0.15 per unit each. If in the same plant, these generators are being replaced by a single equivalent generator, the effective impedance of equivalent generator will be, right? That is 0.05 pu, 0.15 pu, 0.25 pu, 0.45, 0.45 pu. So there are how many generators? There are 3 generators, and the rated is 100 MVA 11 kV, right? So and each having an impedance of 0.15 pu. So let us solve this solution. So applying Thevenin's theorem, you are going to apply a Thevenin's theorem here. Applying Thevenin's theorem, we know that ZTH is equals to can write 0.15 divided by 3, right? So 0.15 by 3 is nothing but what will be the answer? It is 0.05 pu, right? Which is the correct answer here? The correct answer for the question is option A, that is 0.05 pu. Means see here there are 3 generators, right? So how many generators? There are 3 generators. So this is our inductance and having a voltage, that is 3 generators, right? So this is 0.15. So applying Thevenin's theorem, so that is impedance ZTH is equals to 0.15 divided by 3. So 0.15 for all the 3 generators, it is 0.15, 0.15. So 0.153 is equals to 0.05 current. The effective impedance of equivalent generator will be, answer is 0.05 pu. Okay. So next, hi Ratish, welcome to the class. So next question, the pu impedance of an alternator corresponding to base values 13.2 kV and 30 MVA is 0.2 pu. The pu value of the impedance for base values 13.8 kV and 50 MVA in pu will be, right? There are 4 options given: 0.131, 0.226, 0.305, 0.364. So these are the 4 options. Again the same value, that is impedance formula. So we can write now ZPU new, right? ZPU new is equals to ZPU volt kV base divided by kV new. Sorry, it is volt here. kV volt divided by volt square into MVA new divided by MVA volt, right? So now substituting the values. So what is the JPU volt value? Right? So this is our volt value. We write here. Volt is equals to 0.2, right? And kV volt is equals to 13.2, and kV new is equals to 13.8, whereas MVA volt is equals to 30 and MVA new is equals to 50, right? So now ZPU of new is equals to ZPU volt is how much? 0.2 into kV volt, that is 13.2 divided by 13.8 whole square into MVA nu, that is 50 by 30. by 30. So if you solve this, 0.2 into 13.2 by 13.8 whole square into 50 by 30. So what will be the answer here? So the answer of this is 0.305 pu per unit. So which is the right answer here? The option C is the right answer. That is 0.305 is the right answer. Okay. So now moving on to the next problem, that is the reactance of a generator, right? The reactance of a generator designated X is given as 0.25 pu based on the generator's nameplate rating of 18 kV 500 MVA. Based on the generator's nameplate rating of 18 kV 500 MVA. If the base for calculation is changed to 20 kV, if the base for calculation changed to 20 kV 100 MVA, 20 kV 100 MVA, the generator reactance X on new base will be, right? So there are old values given. We have to find out the new generator reactance when it is changed from 18 kV 500 MVA to 20 kV 100 MVA. So now first let us write down the given data. So there are four options, that is 1.025 pu and 0.05 pu, 0.0405 pu, 0.25 pu. Again the same. So here we are going to apply the generator reactance formula, right? So what is the given data here? X old, that is reactance old value. What is the reactance old value? That is 0.25 per unit, right? And next is MVA old, that equals to 500 MVA, right? MVA old is 500 and kV old is equals to 18. kV new value is 20 and MVA new is equals to how much? 100. So now substituting the formula, that is solution X new that is reactance old value into kV old divided by kV new whole square into MVA new divided by MVA base value old base value, that is. So now X new value, that is PU. So X old PU value, that is how much? 0.25 into what is the kV old and the kV new value, that is 18 by 25 square into MVA new is 100 by 500. So if you solve this, we'll get the new reactance PU value, that is 0.25 into 18 by 25 whole square into 100 by 500. So what will be the answer here if you solve this? So that is you get the value as 0.0405 pu. So which is the right option here? 0.0405 pu. So the option 3 is the right answer, right? 0.0405 pu is the right answer. Okay. Next is a three-phase star connected load is drawing a power at a voltage of 0.9 pu and 0.8 power factor lagging, right? Power factor lagging. Then the three-phase base power and base current are 100 MVA and 437.38 amps respectively. What is the current given? 437.38 amps respectively. The line to line load voltage in kV is so we have to find out, right? What is the line to line load voltage in kV? So before that, let us write down the given data. So what are the given? So he has given that voltage of drawing a power at a voltage of 0.9 pu and 0.8 power factor lagging. So we'll write here V is equals to 0.9 pu and power factor is lagging, that is cos pi. Cos pi is equals to 0.8 lagging, 0.8 lagging, and the base power is equals to how much? The base power is 100 MVA, that is 100. You can see here the three phase base power and base current means base power is 100 MVA and base current is 437.38 amps. Okay, so base current is equals to 437.38 amps. Okay, so now solution. So these are the given. So we have to find out the line to line load voltage in kV, right? Solution is, we know that pu value is equals to actual value divided by base value. Actual value by base value, right? Actual value by base value. Therefore, now the base voltage, the base voltage can be written like this, that is base voltage equals to MVA base divided by so we have studied in the previous class all this formula. The base voltage equals to MVA base by √3 into base current. MVA base divided by √3 into base current, right? So now V base is equals to 100 into 10 to the power of 6, right? V base is equals to, that is MVA base, how much? 100 into 10 to the power of 6 divided by √3 into what is our current value, that is 437.38 amps. So therefore 437.38 then V base is equals to base voltage. So if you solve this, 100 into 10 to the power of 6 divided by root 3 into 437.38. So we'll get the value as 132 kilovolts. 132 kilovolts. Now V actual is equals to 0.9 pu into 132 kV. So we calculate this, we'll get the V actual value, that is 0.9 into 132, that is 118.8 kV. Therefore, voltage of line to line is nothing but V actual value. Then VLL is equals to 118.8 kilovolts. Understood? So we have to find out the what he has as the line to line load voltage in kV. The line to line load voltage in kV, that is 118.80. Clear? So three phase base power and base current are 100 MVA 437. So the line to line load voltage in kV is 118.8 kV. Next, moving on to the next problem, that is the per unit impedance of. Hello Surya, welcome to the class. Okay, so now the per unit impedance of synchronous machine is 0.242. If the base voltage is increased by 1.1 times, then per unit value will be right when the voltage base, what is telling, the per unit impedance of synchronous machine is 0.242. If the base voltage is increased by 1.1 times, then per unit value will be, then we can write like this, that is solution. What are the options given here? Options are 0.266 and 0.242, 0.220 and 0.200. Right, these are the options given. Now when the voltage, when the voltage is increased, when the voltage, that is base voltage, right, when the voltage basis is increased by how much? 1.1 times. It has been increased by 1.1 times, then we can write like this, that is kV new is equals to 1.1 kV base, right? Then the new per unit impedance, is, right, when the voltage basis is increased by 1.1 times, the kV new is equals to what? 1.1 kV base. Then the new per unit impedance is what? ZPU new is equals to 0.242, right? This is our per unit impedance, that is volt, ZPU volt, that is 0.242 into so what is the formula? kV volt divided by kV new. So now is telling that it is increased by 1.1 times. So I will take this as 1 divided by 1.1 square. So if you calculate this, 0.242 into 1 divided by 1.1 square, right, kV new means it has been increased, the base voltage is increased to 1.1 times. Base voltage is increased by 1.1 times. Therefore 1 divided by 1.1 square, whole square it is. So I am writing here 1 divided by 1.1 square. So if you solve this, we'll get the answer as 0.2 pu. That is, the right answer for this is option D. That is option for 0.200. Okay. Next problem. For a given base voltage and base volt amperes, the per unit impedance value of an element is X. The per unit value of an element is X. The per unit impedance value of this element when the voltage and volt amperes bases are both doubled is 0.5x, 2x, 4x, or only x. Okay. So this is the given question. He is telling that for a given base voltage and base volt amperes, the per unit impedance value of an element is x. The per unit impedance value of an element is x. So now the per unit impedance value of this element when the voltage and volt amperes bases are both doubled. So what will be the value now? Okay. So calculation. First, let us write down the given data. It's given that ZPU of volt is X. Right, for the given base voltage and base volt ampere, the per unit impedance of an element is how much? X. So ZPU of volt is X. Next, MVA volt, that is for a given base voltage and base volt amperes. So MVA volt will take that as P, right? And now MVA new, that is total power. MVA new, we'll consider it as 2P. Getting this point? Because when the voltage and volt ampere VA bases are both doubled, the new values are doubled, the from the old values, the new values have been doubled. So that's the reason I'm taking here 2P. So next, kV volt is equals to, I can take here V, that is voltage, and kV new is equals to 2V. Okay, therefore solution, therefore, so no need of worrying, just substitute the formula. As we all know, X D, that is of new per unit impedance value of this element when the voltage and volt ampere both are doubled is, okay, X new is equals to X into, this is X into 2P divided by, right, P, that into V divided by 2V whole square. So did you understood this formula? That is X new is equals to X, that is nothing but ZPU old, right? Or else I will write the formula. It is ZPU new is equals to ZPU old, right, into MVA new divided by MVA old into, hi Sundaramurthy, good evening, welcome to the class. MVA new divided by MVA old. Now kV old by kV new whole square. So now substitute the values. ZPU volt is how much? X. So X into 2P divided by 2 sorry, 2p divided by p into kV volt is V divided by 2V whole square. So now PP will get cancelled. So now the whole term, if you calculate here, the ZPU of new value will be 0.5x, right? So 2 whole square, V will cancel, PP will get cancelled. 2 square is 4. So 1 by 4. So we multiply 2 divided by 4. So it will be 1 point, that is 0.5x PU. So the right answer is 0.5x, that is option 1. Okay, 0.5x is the right answer here. So what is telling, for a given base voltage and base volt ampere, the per unit impedance value of an element is X. So that is what we have taken, per unit impedance value of this element when the voltage and volt ampere bases are both doubled. So that's why we have taken their new values as 2p and 2v. And substituting the values in the formula, we got the answer as 0.5x into, that is 0.5 into x pu. Okay. So now next question, that is a 75 MVA 10 kV synchronous generator, 10 kV synchronous generator has XD is equals to 0.4 pu. The XD value in pu to a base of 100 MVA 11 kV is, the options are 0.578, 0.275, 0.412 and 0.44. So let us write the given here, that is given data. So MVA volt, that is equals to how much? 75. Next MVA new, that is equals to how much? 100 MVA, right? Next kV volt is equals to 10 and kV new is equals to 11. So what is the XD volt reactance? That is 0.4, right? So we have to find out the XD new. So solution, write down the formula. XD new is equals to reactance of volt into kV volt divided by new whole square into MVA new divided by MVA volt. MVA new divided by MVA volt. So therefore XG volt is 0.4 into kV volt is 100 divided by 75 whole square into MVA, sorry, kV volt is how much? 10. kV volt is 10, kV new is 11, MVA new value is how much? 100 divided by MVA volt value is 75. So if you calculate this, 0.4 0.4 into 10 by 11 whole square into 100 divided by 75. So if we calculate this, we'll get the answer as 0.44077. So which is the right answer here? The option D is the right answer. Sundar Murthy, the correct answer is 0.44. That is option D. So once check the calculations. Okay. So next move on to the next question. That is the PU parameters for a 500 MVA machine. The PU per unit parameters of for a 500 MVA machine on its own base are inertia, that is M is equals to 20 PU, reactance X is equals to 2 PU. The PU values of inertia and reactance on 100 MVA, reactance on 100 MVA, common base respectively are, common base respectively are, reactance on 100 MVA, common base respectively are. The options are given 4, 0.4. Option B is 100, 10. Option C is 4, 10. Option D is 100, 0.4. Okay. So let us find out the solution for this. The PU parameters for a 100 MVA machine, its own base or inertia M is equals to 20 PU. Can you try this solution, Sundar? Are you there? So the options are A, B, C, D, right? So let us solve this. The PU parameters for a 500 MVA machine on its own base are, that is, so we'll write the formula M PU of new, that is inertia, is equals to M PU of old base value old into MVA of old divided by MVA new. So now what is the M value of old PU, that is 20 into MVA old is 500, right? MVA old is 500 and MVA new is 100. So therefore 500 divided by 100. So if you solve this, 500 divided by 100 into 20, that is 20 into 500 by 100. So what will be the answer? So what will be the right answer? The right answer is 100 per unit. Hi Ramesh. So which question you want to get repeated? So the per unit parameters for a 500 MVA machine. Yes, that's the right answer. 100 PU, right? Inertia of new value is equals to the inertia of base old value into MVA old divided by MVA new. So this is the PU parameters for a 500 MVA. MVA is old value. MVA old value is how much? 500. Machine on its own base. Okay. Then inertia M is equals to 20 PU. This is our old value. Okay. Reactance X is equals to 2 PU. The PU values of inertia and reactance on. So now we have to find out the PU values of inertia and reactance value. That is new values. New values of PU and new values of reactance when the 100 MVA, that is when it was 500 MVA, the inertia is 20 PU and reactance is 2 PU. When it is 100 MVA, what is the PU values and what is the reactance value? That is what we have to find out. So MVA will be our new. The MVA new is what? 100. Understood? So by applying the formula, so substituting in the formula, we got the inertia value, that is PU value of inertia as 100 PU. So the answer will lie between option B and option D now. Okay. So option A and option C has been not in the scenario now. So there is option B and option D available because we got the inertia value as 100 and inertia value as 100. Okay. So let's move on. So let us find out the reactance value, that is X pu of nu is equals to X pu of old X pu of old into MVA of new divided by MVA of old, that is base old, into kV old by kV new whole square, right? So what is the reactance old value? That is 2 pu, right? And what is the MVA new value? That is 100. MVA old is 500. Then 2 into MVA new value is how much? 100 divided by MVA old value is 500. So if you calculate this, 2 into 100 divided by 400, the answer for this is 0.4. Right here, since is telling that the Pu values of inertia and reactance on 100 MVA common base, right, respectively, then we can consider that kV old is equals to kV new. So therefore, it is nothing but 1. So 2 into, neglecting there, I have taken the direct formula, that is 2 into 100 divided by 500, that is 0.4 is the right answer. So now M value we got 100 pu and the new X, that is reactance value. X pu of new reactance value is how much? 0.4. Therefore, the right answer is option D, that is 100, 0.4. So now moving on to the next problem, that is a generator is connected through a 20 MVA 13.8 bar 13.8 by 138 kV step down transformer, 13.8 by 138 kV step down transformer to a transmission line. Where? To a transmission line. At the receiving end of the line, a load is supplied through a step down transformer of 10 MVA 138 by 69 kV rating. A 0.72 pu load evaluated on load side transformer ratings as base values is supplied from the above system. For system base values of 10 MVA and 69 kV in load circuit, the value of the load in per unit in generator circuit will be, right? The options are 36, 1.44, 0.72, 0.18. So now, before going to the solution, let us draw here. So it's telling that a generator is connected through a 20 MVA 13.8 bar 138 kV step down transformer it is, right? So there is a generator, right? The generator is connected to a transformer, that is step down transformer. So it is a step down transformer. So how much it is? 20 MVA. It is of 20 MVA and its ratings are like this: 13.8 by 138 kV, right? 138 kV. Then step down transformer to a transmission line. It is connected to a transmission line. So we'll have bus here, that is A. This is our transmission line. At the receiving end of the line, right? This is the receiving end of the line, is supplied through a step down transformer of 10 MV. There is one more step down transformer here, right? So there is a one more step down transformer in the receiving end, and that is of 10 MVA. This is, we'll take it as T2 and connected to the load. So what is the ratings here? 138 kV, sorry, 138 by 69 kV. 138 by 69 kV. So this is the transmission line. Okay. Now he's telling that a 0.72 pu, a 0.72 pu load evaluated on load side transformer, ratings as base values. This is our load side, right? This is the load side transformer. Ratings as base values is supplied from the above system. From system base values of 10 MVA. And what is the system base value? The total system base value is 10 MVA and 69 kV in the load circuit. The value of the load in generator circuit will be, so the load circuit is given, we have to find out the values at generator circuit, base values at the generator circuit. Okay, so write down base values on load circuit. Base values on load circuit. Okay, what are the base values on the load circuit? That is MVA of base, that is which are the base values? So base values of 10 MVA and 69 kV in load circuit. This side is our load circuit. In the load circuit, the base values are 10 MVA and 69 kV. So let us write down MVA of B, that is 10 MVA, and kV base is how much? 69 kV. Okay, so we have to find out the base values in generator. So before that, okay, load side transformer ratings as base values is supplied from the above system. Okay, so now we have to find out the base impedance first. The base impedance is equals to 69 square divided by 10. I am putting the direct values, that is KVB whole square divided by MVAB, right? Hope you will understand this. 69 square divided by 10. So if you solve this 69 square divided by 10, what will be the answer? 69 square divided by 10, the answer is 476.1. 476.1. Okay, so values of load in ohm is given as impedance ZL, Z in ohm. Values of load in ohm is given as ZL. So that is nothing but ZL is equals to value of load in PU into base impedance. Value of load in PU into base impedance, that is, so value of load in PU, that is nothing but here given, that is a 0.72 pu load evaluated on load side transformer, that is our impedance. Value of load in pu is how much? 0.72 into what is our base impedance we got? So the base impedance we got is 476.1. so if you calculate this, 476.1. Therefore, the load impedance will be 342.8 ohms. 342.8 ohms. Therefore, base values in generator base values in generator circuit, base values in generator circuit, that is MVA of base is equals to 20 MVA, right? MVA of base, that is 20 MVA. A generator is connected through a 20 MVA, right? And kV of base is equals to 13.8 kV. So this is our 13.8 kV. Then base impedance is equals to kV whole square B divided by MVA of B. So we are done already, right? So we'll substitute the value, that is 13.8 square divided by 20. So if you solve this, we'll get the base impedance, that is 9.522 ohms. So therefore, right, the value of the load in per unit in the generator circuit will be value of the load in generator circuit will be therefore you can write like this: the therefore the value of load in per unit of generator circuit will be ZL divided by ZB, right? ZL divided by ZB, the value of load in per unit of generator circuit, that is ZL divided by ZB. So what is the impedance, load impedance we got? We got 342.8, whereas the base impedance we got 9.522. So substituting the values, 342.8 divided by 9.522. So if you calculate this, 342.8 divided by 9.522, so we'll get the value as 36 per unit. So which is the right answer? Which is the right option of this? The option A is the right answer. That is 36 is the right answer. Okay. So this completes the test questions of the previous class. Okay. So now let us move on to the next topic, that is about fault analysis. Fault analysis. Okay. So what is fault analysis? Means we have to analyze the fault in the system. Thus that is called as what? Analyzing the fault. So what kind of the fault will be occurred and how we are going to what you say, recover the fault. So before occurring the fault, what are the protective systems we should be allotted? So all this comes under the fault analysis. So we have to analyze the fault. So if there is a one transmission line, so before doing on a transmission line work, so we have to analyze what kind of fault may occur in this transmission line, and we have to take the protective measures for that. So this is called as analyzing. Okay, so let us start the introduction part. Fault analysis, that is nothing but an abnormality hello right, abnormality an abnormality in the power system. Understood? An abnormality in the power system due to an abnormality in the power system due to what, like short circuit. Due to short circuit will be called as what is called as nothing but fault. Understood? An abnormality in the power system due to short circuit will be called as a fault. Okay, so what we should do, we do the fault analysis, right? So how we are going to do the fault analysis? We do fault analysis to design the breaking capacity of a circuit breaker. So this is a very important point, right? We do fault analysis to design the capacity of a circuit breaker. Understood? So this is very important, right? What is the protective device? Circuit breaker is the first thing where it is going to break the faulty section from the system. So we have to have the good, we have to design the circuit breaker that is its breaking capacity. So what is the fault analysis? To design the breaking capacity of a circuit breaker. Understood? See, suppose if there is a source, that is voltage source, connected to the circuit breaker, and there is a fault, right? If the fault is 1500 MVA, means if this is a transmission line, so in this transmission line we are analyzing that the fault will be of a 1500 MVA. So what should be the breaking capacity of the circuit breaker here? The breaking capacity of the circuit breaker should be 1500 MVA minimum. If it is below 1500 MVA, for example, if the 1500, if the circuit breaker is having a 1400 MVA circuit breaker, then what happens? The circuit breaker will get damaged and the whole system will get damaged. So that's what that is what the second point is. We do fault analysis to design the breaking capacity of circuit breaker. Understood? So why we do this fault analysis? To design the breaking capacity of the circuit breaker. So before, after doing the transmission line, so we have to analyze what are the type of fault, what is the possibility of the fault occurs. So suppose in this line, if there is a 1500 MVA of fault occurring possibility, then the circuit breaker should be designed of 1500 MVA, not 1400 MVA. If the circuit breaker is of 1400 MVA, then what happens? The whole system will get damaged. The circuit breaker will get damaged. Understood? So breaking capacity, the breaking capacity is maximum value is a what? Maximum breaking capacity is a maximum value of power. Breaking capacity is a maximum value of power that can be transferred through circuit breaker. Through circuit breaker. Understood? Breaking capacity is a maximum value of power that can be transferred through circuit breaker. Clear? So what is the maximum value? It depends upon the designing of the breaking capacity. We can design the circuit breaker for 1000 MVA, so that will be the maximum value. If you design the circuit breaker for 1200 MVA, so that will be the maximum value. So that is the maximum power we can transfer through the circuit breaker. That is called as what? Breaking capacity. Understood? And one more thing is, we need to detect the fault location. To detect the fault location, we have to detect the fault location. So this is of fault analysis. What is fault? An abnormality in the power system due to short circuit will be called as a fault here. Understood? So what are the fault? How we can analyze the fault? We can analyze the fault by designing the breaking capacity of a circuit breaker. Right? Breaking capacity is nothing but the maximum value of power that can be transferred through the circuit breaker. Right? This is how we have to analyze the fault. Next topic, that is types of fault analysis. Next topic is types of fault analysis. Types of fault analysis. Okay. So there are two types of fault analysis. There are two types of fault analysis, that is based on line to ground fault, and second one is based on symmetry. That is nothing but symmetrical and unsymmetrical faults. Okay. So in this LG fault, again we have, right? So based on LG fault, in that based on LG fault, we have two types, that is line fault and one more is ground fault. Line fault, in this line fault, again we have line to line fault, right? And one more is LLL fault, line to line fault. Coming to the ground fault, so here we have SLG fault or line to ground fault, line to line ground fault, and LLG fault. So these are the again in the ground fault, that is LG fault, LLG fault, LLL and G fault, triple L G fault. Okay, so these are the based on the LG fault. So in the same way, based on symmetrical, we have two types. One is symmetrical fault analysis, symmetrical fault analysis. Another one is unsymmetrical fault analysis. Unsymmetrical fault analysis. So based on the symmetry, we have symmetrical fault analysis. Another one is unsymmetrical fault analysis. Okay. So now, so there is a one question, that is possible faults. So types of faults you have understood now. So there is one problem, that is possible faults may occur on a transmission line are. What are the faults that may occur on the transmission lines? These are the faults given, that is three-phase fault and LLG fault, LL fault, LG fault. So these are the faults given. The decreasing order of severity of the faults from the stability point of view is. So you have to mention the decreasing order of severity of the faults from the stability point of view. Okay. So there are the four options given, that is 1, 2, 3, 4 or 1, 4, 3, 2, 1, 3, 2, 4 or 1, 3, 4, 2. So this is the option given. So the possible faults may occur on transmission line or which will be the right combination here. The decreasing order of severity of the faults from the stability point of view is. So the right answer for this is option 1, that is 1, 2, 3, 4. 1, 2, 3, 4. That is three-phase fault, L2LG fault, L2L fault, L2G fault. Okay. See why? Because there are different types of faults in the power system. There are different types of faults in the power system. We have studied, we have read in here, right? There are line to ground fault, line to line fault, line to line ground fault, and line to ground fault. Okay. So like for example, that is, it is called as what? So these are the given faults here, right? So there are different types of faults like single line to ground fault, okay, line to line fault, double line to ground fault, three-phase faults, that is LLL or LLLG faults. So now among the given faults, I can tell here why, because among the given faults, which are the given faults here? There are four options, right? Three-phase fault, line to line ground fault, line to line fault, and line to ground fault. There are, so LG, that is line to ground fault, is most common, is a most common fault. Is most common and occurs frequently, Which one? Line to ground fault. Understood? So line to ground fault is the most common and occurs frequently. So the order of frequency of occurrence is like this. It will be the line to ground fault is more than line to line fault, right? And line to line more fault is more than line to line ground fault, then that is greater than LL. So that's why the option 1 is the right answer here. Understood? So among the given faults, right, there are four faults. The most common fault is line to ground fault. So decreasing order of severity of the faults. So three-phase fault appears very rarely. and next comes L to LG fault, then L to L fault. Line to ground fault is very common occurring fault. That's why they have given here. Line to ground fault is more than line to line. Line to line fault is more than line to ground. Double line to ground fault. Double line to ground fault is more than the triple lines. Okay. Next. Match the different unsymmetrical fault currents. So there are unsymmetrical fault and there are fault currents given. So unsymmetrical fault, line to ground fault, line to line fault, double line to ground fault. There are equations given. So we have to choose which is the right answer here. The options are A2, A1, B2, C3, A3, B2, C1, A3, B1, C2, A1, B3, C2. So these are the options given. So we have to match the right one. So which will be the right answer here? Right? Unsymmetrical faults. So the right answer for this question is option 3. That is A2 3. That is A2 3 line to ground fault. Next B2 1, that is line to line fault, and C is 2 here. So line to line ground fault is IF is equals to 3 IA naught. Okay. So let us see now. So single line to line ground fault, single line to line ground fault. So here the single line to ground fault occurs when one conductor falls to the ground or contact the neutral conductor. Then only will the ground fault will be occur. That is LG fault. So when this LG fault occurs, so this LG fault occurs when one conductor falls to the ground. Okay, the 70 to 80% of the fault in the power system is single line to ground fault. That is what we have discussed. 70 to 80% of the fault will be single line to fault. It is very commonly occurring. Okay, so that's why. So therefore, we can write like this: IA naught is equals to IA1 is equals to IA2, right? So that is nothing but sequence 3. We know that what symmetrical and unsymmetrical, right? There is IA, IB, and IC. That can write is as IA1, IA0, IA1, and this is IA2. So which type of fault it is? Unsymmetrical fault, right? So now IA0 is equals to IA1 is equals to IA2. So this can be written like this. That is the field current IF is equals to 3 IA0 is equals to 3 IA1 is equals to 3 IA2. Got it? So 3 IA0 is equals to 3 IA1 is equals to 3 IA2. Then IF is equals to 3 EA divided by Z1 plus Z2 plus Z3. Understood? So this is of LG fault. In the same way, coming to the line to line fault, so we can write that is IA naught is equals to 0 and IA naught is equals to 0 and IA1 is equals to minus IA2, because in the line to line fault, positive and negative sequence connected in series opposition, right? the percentage of such type of faults approximately is 15 to 20%. So there is a equation that is line to line fault IA0 is equals to 0 and IA1 is equals to minus IA2. So both are connected in series opposition, positive and negative sequence connected in series opposition. So we know that IF is equals to root 3 IA1, that is equals to root 3 IA2, right? Then IF is equals to root 3 EA divided by Z1 plus Z2. So this is option, that is line to line fault. IF is equals to root 3 EA divided by Z1 plus Z2. Next, in the same way, double line to line ground fault, that is LLG. So that is, there is a equation for that, that is IA0 plus IA1 plus IA2 is equals to 0, where VA0 is equals to VA1 is equals to VA2, right? So therefore, IF is equals to 3 IA0, right? IF is equals to 3 IA0. So that is line to line ground fault is IF is equals to 3 IA0. So match the different unsymmetrical fault. These are the equations of line to ground fault, line to line fault, line to line ground fault. I have just given the brief idea of the equations. So in further classes, we will be solving this in very briefly. Okay. So next, moving on to the next question. The power system is subjected to a fault which makes the zero sequence component of current equal to 0. Right? The power system is subjected to a fault which makes the zero sequence component of current equal to 0. The nature of fault is, so what will be the right answer here? Double line to ground fault, double line fault, line to ground fault, three phase to ground fault. So okay, so before solving this, so we have to understand what is zero sequence component, right? So there are three sequence of components, that is positive sequence component, negative sequence component, and zero sequence component. So these components are used, these sequence components are used to rectify the unsymmetrical faults. Okay, to rectify the unsymmetrical fault analysis, we have using the sequence method, that is positive sequence component, negative sequence component, and zero sequence component. So let us solve explain about the what is positive sequence component, negative sequence component, and zero sequence component. So here positive sequence component, positive sequence component so it has three vectors. Positive sequence component has how many vectors? It has three vectors. It has three vectors. It has three vectors of equal magnitude. Equal magnitude. Understood? That is, for example, VA1, VB1, VC1, right? Then it has three vectors of equal magnitude, but displaced in phase from each other by what will be the angle? It is positive sequence component is telling that it has three vectors of equal magnitude but displaced in phase from each other by 120 degree, right? So I'll draw here, for example, if this is VA1 and this will be VC1 and this is VB1. Okay, VA1, VB1 and VC1. This is of positive component. For it has a 3 vectors of equal magnitude but displaced in phase from each other by 120 degree and has the same phase sequence as the same phase sequence as the original vectors clear that. So it shows that what is the positive sequence. It shows or it specifies that the current is flowing through the current is flowing through the current is flowing through the source to load. Understood? So this is of positive sequence component, that is it has 3 vectors of equal magnitude but displaced in phase from each other by how much? 120 degree. The magnitude of here VA1, VB1 and VC1 is same, but the angle is 120 degree, right? The phase sequence has the original vectors and has the same phase sequence as the original vectors. So it shows that current is flowing through source to load. So this is of positive sequence component. So whereas negative sequence component, negative sequence component, the negative sequence component, even it has a 3 vectors, right? It has 3 vectors. It has 3 vectors of equal magnitude, right? Same as positive sequence, has equal magnitude but displaced in phase from each other by 120 degree. It is also displaced in phase from each other by 120 degree as of the positive sequence component, and the phase sequence and the phase sequence opposite to the original vectors. So understood here the difference between positive sequence and the negative sequence. In the positive sequence, the phase sequence is same as that of the original vector. So whereas the negative sequence component, the phase sequence opposite to the original vectors, So it specifies that current is flowing from load to source. Current is flowing from load to source. Understood? So in the positive sequence, it shows that the current is flowing through source to load, whereas in the negative sequence component, the current is flowing from load to source. So here the phase sequence in opposite to the original vectors. Okay, their magnitude are same. Their magnitude are same. This is IA1, right? And their magnitude will be same. Actually, this should be opposite, right? So IA1, IB1 and IC1. So instead of IB1, it will be here IC1 and this is IB1. That is the phase sequence opposite to the original vectors. So they will be displayed by 120 degree and they will be having the equal magnitude, but the phase sequence is opposite to the original vectors. So it specifies that the current is flowing from load to source. Okay. So this is of negative sequence component. So next is zero sequence component. Next is zero sequence component. So it has three vectors. Again the same. So even it has three vectors. Here what happens? Of equal magnitude. Of equal magnitude. It is a zero sequence component. Understood? So there is no. So there is no values. That is three vectors of equal magnitude and also or in phase with each other. Very important point here. They are in phase with each other. So they are not displaced in phase from each other by 120 degree. They are in phase with each other. Means they are all the three vectors of equal magnitude and also they are in phase with each other. Understood? So it specifies. This is called as zero sequence component. Here there is no angle, they are all in phase. So that's why it is called as zero sequence component. It specifies that the current is flowing. Current is flowing from source to ground. Current is flowing from source to ground. Current is flowing from source to load. Okay. So these are the three vectors. So they are in phase with each other. They are in phase with each other, but their magnitude will be same, equal magnitude, but in phase with each other. Okay. The power system is subjected to a fault which makes zero sequence component of current equal to zero. The nature of fault is, right? The nature of fault is. So what will be the fault here? So the zero sequence component is telling that it has three vectors of equal magnitude and also are in phase with each other. So therefore it specifies that the current is flowing from source to ground. The current is flowing from source to ground. Okay. So now, so by seeing this, we can consider that positive sequence components exist in both balanced and unbalanced conditions, right? It can exist in both balanced and unbalanced conditions, whereas the negative sequence components exist only in unbalanced conditions, and whereas zero component exists in the unbalanced conditions involving ground fault. Right? Therefore, in double line fault or line to line fault, there is no ground. Understood? So zero sequence components exist in unbalanced conditions involving ground is telling. The power system is subjected to a fault which makes the zero sequence component of current equal to zero. The nature of fault is double line fault. This is the right answer. Understood? So in double line fault or line to line fault, there is no ground, right? Therefore, the zero sequence current is 0. Getting this point? So zero sequence component. So the zero sequence component will appear at what? It is involved in the ground. So therefore, the current, right? The current equal to 0. Where the current will be equal to 0? The current will be equal to 0 during double line fault. Understood? So moving on to the next question, that is, a dash is a series type unbalanced fault that occurs in power system. The options are line to line fault, double line to ground fault, and single line to ground fault, open conductor fault. Dash is a series type unbalanced fault that occurs in a power system. The right answer is open conductor fault. Open conductor fault is a series type unbalanced fault that occurs in a power system. Okay. So why it is? So there are types of open circuit faults, right? So there are types of open circuit faults. In that is a single phase open circuit fault, two phase open circuit faults. First one is single phase open circuit fault, and second one is two phase open circuit fault, and third one is three phase open circuit fault. So these are the different types of open circuit faults. So it's telling that in a series type, unbalanced fault that occurs in power system is open conductor fault in a series type, right? So open circuit faults means what? Open circuit faults are also called as series faults. Okay, open circuit fault also called as a series faults. That is the reason we are taking that open conductor fault is right answer. Here you will write the point here. Open circuit faults. So in open circuit fault, there are three types: single phase open circuit fault, and two phase open circuit fault, three phase open circuit fault, right? Open circuit faults are also called as series faults. Open circuit fault are also called as series faults. Okay, so these are unsymmetrical or unbalanced type of faults except three phase open fault. Understood? Next question. The percentage resistance of a 100 kVA 5 kV 5 ohm reactance is given by, right? The percentage resistance of a 100 kVA 5 kV 5 ohm reactance is given by, the options are 2%, 20%, 40%, and 4%. Okay, so here let us write down the given. So he has given that base MVA, that is base MVA is equals to 100 kV, right? The base MVA, that is percentage resistance of 100 kVA, is given in kVA. So base MVA is equals to 100 kVA. So if you convert that into 100, that is divided by 1000, then it will be 0.1 MVA, right? 100 kVA means we have to divide by 1000, then we can convert into base of MVA, that is 0.1 MVA. Base voltage is equals to how much? 5 kV, right? Next is given resistance. The resistance is 5 ohms. So what is the percentage of resistance? percentage of resistance 2%, 20%, 40%, and 4%. So let us apply the formula, that is solution ZPU new is equals to ZPU of old into MVA divided by kV base square. MVA base kV base square, right? Then 5 into, that is MVA base is 0.1 divided by K is 5 square. So if you calculate that 5 into 0.1 divided by 5 square, we get the new value as 0.02. So therefore ZPU percentage in percentage you can write 0.02 into 100. So then what is the answer? 2% is the right answer. So option 1 is the right answer here. Okay, option 1 is the right answer. Next question, irrespective of the causes, which is the fault in a three-phase system? Irrespective of the causes, which is the fault in a three-phase system? So there are option given: unsymmetrical fault, both symmetrical faults and unsymmetrical faults, symmetrical faults, external faults. So irrespective of the causes, which is the fault in a three-phase system? So that nothing but simple, that is nothing but both symmetrical faults and unsymmetrical faults, right? Irrespective of the causes, which is the fault in a three-phase system is unsymmetrical and symmetrical faults. So let me tell some few points of the symmetrical faults. It is a fault where all phases are affected, so that the system remains balanced. Okay, this is the first point. And the second point, it is a fault where all phases are affected so that the system remains balanced. It is a symmetrical fault, means system remains balanced, means the phases, like all phases will be having 120 degree, 120 degree, 120 degree. If you occur the fault also, the system remains balanced condition itself. The system remains in the balanced condition itself. Okay, a three phase fault is a symmetrical fault. Which fault is called as symmetrical fault? A three-phase fault is called as symmetrical fault. So where does this symmetrical fault occurs? This symmetrical fault result in balanced conditions. Understood? All the phase will be balanced. All the three phases will be balanced. The fault occurring at the balanced conditions is called as what? Symmetrical fault. Balance conditions. So they may be analyzed. They may be analyzed they may be analyzed using per phase analysis. By using per phase analysis. So this is of symmetrical fault, right? And unsymmetrical faults. So unsymmetrical fault. This fault lead unequal currents. This fault lead unequal currents with unequal phase shifts. Unequal phase shifts in a three-phase system. Understood? So these are the symmetrical faults and the unsymmetrical faults. Both occurs irrespective of any causes in the three-phase system. So that is the answer, both symmetrical faults and unsymmetrical faults. Okay. So even it can occur either by natural disturbances or by manual errors. By manual errors. Okay. And this unsymmetrical fault occurs in a system this unsymmetrical fault occurs in a system due to the presence of an open circuit or short circuit or transmission or distribution line. So these are the few points of unsymmetrical faults. Okay. So the right answer for the question is both symmetrical and unsymmetrical faults. So in the unsymmetrical faults, this fault is led unequal currents with unequal phase shifts in a three-phase system. right? It can occur either by natural disturbances or by manual errors. This unsymmetrical fault occurs in a system due to the presence of an open circuit, or it may be a short circuit, or transmission line fault, or distribution lines. Okay, so this is of symmetrical and unsymmetrical. In the next coming class, we'll be discussing many more things about the power system topics. So today's class, we'll end this today's class. Good night, everyone. Thank you.